Professor Dan-Adrian German from Indiana University in Bloomington, right?
That's right.
So you're in the computer science department studying quantum computing. I know you from the Quantum Science and Engineering Education Conference, where you've presented a number of times on different strategies for teaching. So it seemed appropriate to invite him here. And I'll hand it over to you.
So this is the conference that she mentions. I'm in one of them. And hello, thanks for inviting me here. So once again, my name is Adrian German, and I'm from Indiana University, Bloomington. I hope you can hear me well. If so, we can get started. The title of my presentation is Jumpstarting Quantum Computing in the Middle and High School Classroom, a guide for teachers and learners. At this conference, which was in Montreal, that was in September, we presented our efforts and results towards putting together a faculty learning community in quantum information science for high school teachers. And we work with CSTA Indiana, which is the Computer Science Teacher Association for Computer Science in high school in the state of Indiana. The co-authors that you see over here are basically some graduate students and some undergraduate students and then some high school teachers. Now, I would like to give you some background. Jake was chair of the Workforce Development TAC last year, and before that he was the vice chair. And I also had the honor and, I guess, opportunity to serve as a chair of the Workforce Development TAC in quantum, the QEDC back in 2021. Charles Robinson was my vice chair at the time. So at the time, one thing that I wanted to do, because I was in computer science, I wanted to do many things, but with respect to computer science, you have to know that there is an organization called ACM, which is quite big. And then there are some other organizations which are just as big, but they have other purposes as well, IEEE Computer Science and also AAAI now. And since '68, every 10 years, they get together and they put together a guide for the curriculum. If you are a department somewhere and you want to establish a program, or you want to change your program or update your program, there are knowledge units and ways in which you could implement them, and how you would update them, and what exactly you can do to make sure that your this is everywhere in the world. Your graduates are going to end up with the skills and the knowledge that will make them successful. So it started in '68, and it was about every 10 years. The last time before the time when I was part of it was in 2013, and there was nothing about quantum computing, but perhaps understandably so. So what I wanted to do during the time that I was chair, I wanted to communicate with the Board of Education from the ACM as well as IEEE Computer Science to see if we, the QEDC, if I could possibly be the liaison between the QEDC with all those members, industrial members and agencies and government agencies and academia, to see if we can influence the curriculum so that they would have a knowledge unit about quantum computing. And at that time, when I called them, they were in flux. They were changing the boards of education. So back in, after a year in 2022, when I called them again, they said, yes, we have everything worked out. Why don't you join us? So I was a liaison between the QEDC and them. We wrote a paper, which you can see over here, that we presented at CXC. CXC is a big conference for computer science education, special interest group in computer science education. This was in Toronto. And we tried to do the best we can to propose a set of learning outcomes and topics such that people would be at least become aware of what's available. We encounter a lot of opinions. For example, it shouldn't be too much physics. If you have physics, people are going to run away. They're going to be scared. It's too complicated. If you start physics, you never finish it because it's connection with everything, and it's exciting, and they never come back and stuff like that. So we said that there must be some sort of understanding of what quantum mechanics does, but that you shouldn't know it in detail unless you end up building things. And other than that, you should just go proceed with what we proposed over here. So we looked at three different things. One was let's say we started with the Vazirani course, which was also available online in edX. There were lots of courses, still there are, available, MIT X Pro and so on. And then we looked at them, and some people in the QEDC actually created their own course, and that was Diana Franklin from Chicago. And she has a 2-part course, which is excellent on edX if you want to take it. And after that, we decided that that would be the golden standard. Let's say the Vazirani course from Berkeley, which is a 100 level class, 191. But that some people might want to do a 2-semester class, and some people might want to do a shorter version class. For example, first-year seminars are 6 weeks with us in Bloomington. But we frequently have 8-week classes, which is half-semester class. Now, the first thing that I say over here is a quote from Scott Aronson, who said quantum computing is really, really easy if you take the physics out of it. So that supported the vision of the computer science that is just a formalism, which is exciting, and you really shouldn't get there because you need the additional intuition, which you may not have as a computer scientist. The truth is that for years, computer scientists, let's say undergraduates, have been used to the idea that to succeed, you just need a little bit of discrete mathematics and coding, which I think is false, but that's what they think. And as a result, they don't have a strong background in anything. But they are eager to code. So, so what did we think that we should have here? Again, some kind of literacy, and then an appreciation, and then know where you're good to go if you're really going to be serious about building things. So that's the paper that we wrote at the time. And then we did it backwards. We collected information, and we sent a survey to QEDC. We collected information. Jake helped me and a few others. Got the data. We processed the data. We explained how we think that the data supports our view. And then there were some interesting things in the data. We published that as a poster. I mean, we presented as a poster at ETXC next year. Same year, but in summer in Finland. That was the European version of 60, so to speak. And that was pretty much it. Now, there is a knowledge unit on quantum computation in the CS 2023. And hopefully 10 years from now, whoever gets to do that will do it even better and deeper and so on. But we have a foot in the door in some sense. So the question now is, how are you going to do what you said we should do? How would I do it if I agree with you that I should do it, but I haven't done it before? And so what I would like to describe to you today is the way I have been teaching it for a mixed audience that I'll describe in a second as well, for the last 3 or 4 years. In addition to the fact that I was trying to put together a curriculum for undergraduates, I was part of it, but that was not the main factor. We put together, again, the physics department was the main driving force here, a master's in quantum information science, which is an accelerated master, so it takes about 1.5 years to finish it. It's for the people who have graduated a STEM major, but not physics. Essentially, what they wanted to do is to establish a boot camp so that when they come without the physics background, they can still connect to, let's say, and be able to take P555, which is the first course in the master's, Nielsen and Chuang. So I have a quote somewhere over here, and I'll show you a little bit later. I wrote a paper instead of slides. I have slides too, but I might take you through the paper. The quote here says that if you are convinced that you can't do math, you will be able to not do it, whatever it is that you recognize as being math. So we had this issue with people coming in and say, I'd like to learn this. Oh, but there's something that I should have taken when I was younger, but I didn't, so what do I do now? Because I want to learn it immediately. So for people who are, in fact, missing any amount of appreciation for math, or because they weren't exposed to it, or the actual fluency, we need to come up with some compromise. And then I realized that if our students are very, very young, they didn't even have the opportunity to take any math course. So that's the mixed audience that I am catering to. Either students who are so young that they haven't seen math, therefore they can't possibly use it, but they like to learn it, and they will. Or students, sophomores, for example, in computer science, who thought we were told some discrete math is going to be enough. But then it turns out it's not like that. So I start this thing that is somewhere in here that I can show you at some point. So from this page, which I wrote for this workshop, I can go to all the things that that I could share with you, and I can show you much more. And I said, if you look at dogs catching a frisbee, you have to say that they know physics. Sophomores are good at that too. They also have short attention spans. So there's some sort of similarities between the two groups. They're very intelligent as well. Do you think that they are catching the frisbee by solving equations? No. Then do you think they learn that physics that allows them to catch the frisbee in a classroom? Probably not. Then what did they do? Well, experiential learning. So they want to practice and do it and then get used to it. So for dogs, for example, I believe the theory now is that there is embodied heuristics. They only have to do, if you're a dog and you've been doing this for years to catch prey or whatever, is to basically be sensitive to the angle of your gaze to the thing, and then that will tell you if you should slow down or run faster. So how can you build an intuition if you're going to teach them, because that's how they are. I can't teach the dogs. There is a book, How to Teach Quantum Physics to Your Dog, but it's just a clever title. But I would like to teach quantum computing to my sophomores, and I think I have to keep the dog model in mind. And I think that they prefer to build this intuition. But the intuition necessary for quantum computing is based on quantum mechanics. They do not interact with it on a daily basis because they are so big. However, the frisbee is easy. You just go outside and play, and everything is classical. And you get to play, and then you pick it up. So I said, because I'm writing here mainly, I'm writing to whoever reads this, but I'm writing to a computer science audience. I said, you should not be afraid to bring up physics, because the only way to get in touch with the intuition that you would build if you were to be in that world is through some sort of lab equipment. Lab equipment is very expensive. The Thor Labs equipment is expensive. But there's Quantum Fly Trap, which is available online. Arthur Eckert is the scientific advisor. There's a group in Poland, a group in Oxford, and it works very well. And I have some pictures in there that you can see. And I also have a link a tab to it. Flytrap is right here. So you go into the virtual lab, and you click here, and you say, perhaps I want to study entanglement. You click experimental setups, and you find there's lots of things. They sell themselves as being free. They sell themselves as being a no coding IDE for quantum computing. And if you say spooky action at a distance, when you start playing these things, you get to see what is happening. So this passed through the filter. And so the other one got a state which will allow it to go there. I have one here and one over there. This one here passes. That one goes into the same kind of state, 2-2. And then when this one will be trapped, there will be a different state over there, which will make it go through the other receiver. And in this case, for example, there's one here. There will be one over there, and then there's two here. Can make it faster and so on. But at least you get to tell them, watch out. We have superluminal correlations, but this is not causality. And they get to play. They get to play with lots of things in this environment. It's free and perhaps interesting for them. And it satisfies what I think they need to see. They need to be somewhat literate about what's happening in there. You may remember that back in 2020, Kavli organized a conference, and then they said, what should be the main, some people in this room were there, what should be the concepts that every learner should be aware of at the very beginning? And they came up with 9 concepts. And those concepts are like superposition and entanglement and quantum information science and collapse and interference and so on. So this is what this is catering to. Great. So now what I would like to do now is to tell you that as I started with Vazirani formalism, which is essentially, I'm just going to say that now my go-to book is the book by Tommy Wong, because it's available online so good, and you have such a great presence online, and it's free. So I say this is an excellent book. But as I said to you before, if they think they can't do math, then they are going to be turned off by those equations, which is unfair, which is not real, but that's what happens. So I said, what else can I do before that? And even back in 21, we were talking about Terry Rudolph's book, Cues for Quantum. I have a copy over here. It's not that big. He published it by himself. Since this workshop is like in its third year or so, who knows if somebody hasn't come here before to talk to you about this approach? I don't. Okay. So Terry Rudolph is one of the founders of PsiQuantum. He was born in Australia. He grew up over there and in Africa. And then he went for his PhD in Canada. And then he's teaching now in London, but also is involved with this company, which now is moving to Chicago. Not the whole company, but just a big part of it. So I would like to play. So I say, well, have you read this book? Well, have you, hopefully, but maybe you haven't yet. It has 3 parts. You can have all the book here on this website. You see, part 1, part 2, part 3. Part 1 is Q computing, he calls it. Part 2 is Q entanglement. Part 3 is locality and Bell equations. So you can get the book from there, but you can also get it from Amazon or whatever, or some other place. This is for free, though. And you can read it. And the question is, if you haven't, then what can I do for you so that I can get as the next best situation? I have this video. So I'm going to play this video. My tendency is to play it all. If I play it all, that's 20 minutes. I think for a group like this, 20 minutes is probably extremely long. I still have this idea of playing it all, because then we will have a common reference. And then I can give a set of exercises, and I can solve them for you, too. But the point here in this video is that he is talking to an audience that is 6th grade or 7th grade. I was told by people who I know have watched this last night that it's too detailed and that it could be done in much smaller amount of time, much shorter amount of time, which is a positive comment. It's meant to be that obvious. So I would like to start at least to play it a little bit, and then maybe if it's really slow, I'm just going to take over and then say the same thing and then give you the equation. So here's the video now. I think they have to, I'm going to start playing it, okay? This is Terry Rudolph.
I want to teach you the first mystery.
Let me ask her if, she said she has to adjust the volume because it's too loud. Can I? Where?
G'day folks. Today I want to teach you the first mystery of quantum theory. Quantum theory has many mysteries, but this is the first one. It's the most special. I'm going to teach it to you using...
That's all right. Just put it over there. But it doesn't work.
Oh, it doesn't work?
Yeah.
Oh.
So
teach it to you using only basic mathematics. And I'm not just going to give you metaphors and analogies and stories. I want to teach you the actual quantum theoretic description. Now, we'll start off by talking about a very simple system, which is going to be just a ball. And this ball can be either black or white. You might be thinking, hang on, quantum theory, isn't that about like atoms and photons and tiny things? And it's true, that's where we mainly use it. But if the laws of quantum theory are correct, in fact, they apply at any scale. And so, although the experiments I'm going to describe to you in practice we do slightly differently, in principle, they can be performed exactly as I describe. So we have this ability to take this ball, and it can be either black or white. So this is going to be the white ball, and this is going to be the black ball.
So clearly he means his chalk has ink, right?
And we have many of these balls, but what we're going to do is we're going to drop them into a box. And this box kind of has a hole in the top and a hole in the bottom. And the label on this box is going to be not. Okay, strange label. But what we find is that when we drop a white ball into this box, it comes out black, like this. So we drop the ball in here and it comes out here black. Conversely, if we drop in a black ball, then it comes out here white. So that's the origin of the name not for this box, is that the color that comes out is not the color that went in. It's a slightly funny name. So black goes to not black, i.e. white, and white goes to not black, i.e. black. Okay, so the not box just does a very simple thing. We don't actually ask the question what's going on inside this box. We just know that the effect on the color of the ball is to change the color. So here's the first question for you. What do you think happens if I take two of these not boxes and stack them one on top of the other? So I'm going to take not box number 1. It's got a hole in the top and a hole in the bottom. And then not box number 2, which also has a hole in the top and a hole in the bottom. And I'm going to drop, let's say, a white ball into the top of the first not box. What do you think is the color of the ball that we see?
So that's a very simple question, but basically that's how the video goes. I'm going to tell you something, let me ask you a question, here's the answer, move on. The purpose of the video is to introduce the Hadamard gate. So I still want to play all of it, except I want to tell you things about it as we proceed. I'm going to go here, but not here, wait a minute. I want to go here, but then I'm 3:22 into the video, and if it turns out to be difficult, I will not play it anymore. I would like to go to this. So I'm going to say that in the thing I wrote for you for today, which you can find out if I send it to you, he's going to go over basically the following diagrams. This is the NOT gate that you've seen already. This is a classical gate. It's not a big deal. It's a simple thing, but you get used to the idea of a blob that has white or black. A little bit later, he introduced the C-NOT. The C-NOT has 2 inputs. One is a control, the other one is a target, and he describes how things happen. You see how 4 cases. And then you say, but really, the C-NOT works on arbitrary qubits. What do you do in that case? And the answer is, in his book, he doesn't use any coefficients whatsoever. So then you might say, first of all, maybe he's not going to give me the whole story. That's not nice, but he does. And furthermore, I won't be able to get to the whole story because he doesn't use probability amplitudes anywhere. That's true, but the surprise remains that his system is so effective. I'm going to show you in a second how effective it is. And then he's doing what he was asking you just now. What if you stack them, two NOT gates on top of each other, and clearly the ball comes up the same color that it went in. Now, how did he come up with this? He was in London, he was in the subway, and he was going to a summer camp that was middle school students. Pete Shadbolt was in charge of that summer camp. So he realized that with C-NOT, with NOT, C-NOT, and Hadamard, he gets universal quantum computation, except for the fact, in some cases, with arbitrary precision. In other words, you can calculate anything you want, but with a small overhead. So he said, from a certain point of view, it's okay if I give the kids these gates. I just have to teach them to work with them. So he went there, but he didn't call the Hadamard gate Hadamard. He called it a Pete box, because Pete was in charge of that summer camp. That's why in his pictures you're going to see Pete boxes, not Hadamard gates, which is, by the way, also very long, the name. So he basically says in the video, what happens if you put white balls in a Pete box? And the answer is, if you look at the answer, if you look at the outcome, you're going to get black and white in the same proportion. So it's random, as far as we can tell when we look at them. But what if you put black balls in it? Then it comes out random as well. He has the same idea. Why don't we stack them? And now the problem is, do you look or you don't look in between? As if you look, you ruin and it's random, but if you don't look, you get the same ball back. How come? And the purpose of this video is to introduce a superposition idea and to show them how to work with the Hadamard gate so that it in fact recovers the ball that came in. For this, he uses this operator. He says, I'm going to, and I'm going to let him say it. I'll tell you ahead of time what to expect, and then I'm going to let him say it, and then we'll solve a problem together, and then we'll see what else we're going to do. But he has this cloud that says, if you put a white ball, what I'm going to tell you is that you get a state that is hard to describe, so physicists invent words. Superposition is a word for this, such that what this shows is that if you measure, you get white or black with the same probability. And if you put a black ball inside a pit box, then you get that cloud. And he says, I can't tell you why the minus shows up here, but nobody else can. And you have to assume that it's a phase, and it's only a certain type of phase. And when you measure, you still get white or black. So the exercise that I want to give you after we finish watching the video is this. My goal is not for you to learn his system, even though I think that that's easier. My goal is for you to learn his system so you realize that you don't hate mathematics, or you don't hate the formalisms, that things can work out for you. And then if you open a normal book, such as this diagram, and you say, what's H? That's the pit box. Oh, okay, I know that. What's X? What's Z? Oh, you didn't define Z for me. So I'm going to define Z for you just now. What he said with respect to, so far what we know, is that X of white is going to be white. That's what he told us. Oh, sorry, black. And my black is black. So X of black is going to be white. And that's the definition that he gave us so far. What he gave us are the columns of the matrix that define X, which we were shown yesterday too. So what is the Z, which he never defines in the book? He doesn't need it. Z applied to white leaves white unchanged. And then Z applied to black is going to give me a negative black, which I'm going to write, if you don't mind, as a black with a line on top, just to save some space. So with this, I could basically ask you to show me that Z of white is in fact white. And that's super easy. Or Z of black is in fact black. And that's also easy because the minus shows up and then it disappears. So when you look at the thing that I showed you, it was with, it says, if you have a 0 over here, which people by now, I'm telling them, should be the white ball. And if you have a 1 over here, then you know that X is going to take you from one to the other, both ways. And we don't know how to do the pit boxes yet, but Z is going to apparently take you between these two states. What are those states? Let's say that we immediately picked up the H gate is going to put you into a plus state. You have been saying all through this workshop, which is totally fine. And the plus state actually looks like this. But it's kind of uncomfortable to keep drawing these clouds. So I'm not going to draw them like that. I'm going to erase them, and I'm going to say I'm going to mark them as a curly brace with the two outcomes inside. This is a superposition state. So what do you get when you measure? One of those. So if you see a comma, the order doesn't matter, because it's what I would get if I were to measure, whichever of the two. And why do you think they are equally likely? Because they seem equally likely. So another state that I could have, for example, could be this, right? I think in this state, you probably would argue that maybe the white is more likely to come out when you measure. That's true. Maybe you say, but I don't know how to write that in the standard formalism. Well, I'll show you. And so on page 83 of his book, he has the only numerical rule in his book that says, if you give me a misty state, I can teach you how to calculate actual representation by calculating the probabilities and then take the square root so you can put the coefficients in front of them. Okay, so what I'm trying to do over here is essentially to show you that these transitions minus hold. According to the rules that we had so far, these are our representations. I think you're convinced about X. Are you convinced about Z? Do you think Z is going to take plus into minus and minus into plus? You say, you didn't give us all the rules. What rules have I not given you yet? Well, you didn't tell us. First of all, you didn't let us watch the video so we can get the superposition exactly as Terry explains it. But if you say, but that can be understood, you didn't tell us what happens when, say, Z is applied to a superposition. And so that's the linearity requirement. It should preserve the sum. It should take the scalar out. So the basic idea behind this is that if you have a gate applied to a superposition, you basically have the superposition of the gate applied to the individual states. So you could say something like this. Z applied to this guy is going to be equal to a superposition, I said, of Z applied to white and then Z applied to black. And you know how this works individually. And he doesn't do Z in his video or in his book. So if we go back to the video, we'll get to see something that I haven't done yet. So this is going to be white, and then that's going to be negative black, which we decided I can write by saying put a hat on top, or whatever, a beret on top of this guy. So I have shown you this. You were convinced of this and this. We kind of understand this by definition. And so we have just a few of these arrows to prove. Can we switch back to the video? So far in the video, he didn't do much, but I claim that what he has done so far has enabled me to introduce things to you. So if we were to go back to the video over here, wherever that is, it's in here.
It comes out white because when it went through the first knot box, it emerged black. And when it went a black ball going into the second knot box, flipped it back to being white. So the combination of two knot boxes, in fact, doesn't do anything to the color, because similarly, if we dropped a black ball in, then it would automatically emerge black. It would flip to white after the first one, and then from white would flip back to black. Okay, so the knot box is not a particularly mysterious box. Okay, but there is a box that we can build which we do find really mysterious. It also has kind of a funny name, and the name is not particularly elucidating, so I'm just going to call that box after my friend Pete, who has built many of them. I'm going to call this the Pete box, and the Pete box also has one hole in the top and one hole in the bottom. And when you drop a white ball into the top of the Pete box, what you find is that some of the time it comes out white and some of the time it comes out black from the bottom. So maybe the first time you drop the white ball in, it comes out white, but maybe you drop a second white ball through and that one comes out black, and so on. So you can drop many white balls through the Pete box, and you just find some of the time they'll drop out white, some of the time they'll drop out black, and so you get it just a mixture. And we find there's no pattern to whether they fall out of the bottom black or white. It just seems to be exactly the same as if you flipped a coin. We look for patterns, we've never found any. Now similarly, if we drop a black ball into the top of the Pete box, they also come out the bottom randomly black or white. Some of the time white, some of the time black, every single time just seems to be completely independent and just completely random. Now you could say, well, that's not a particularly strange thing. It just means that what we have going on inside the Pete box is just something noisy, something strange, something kind of random, and you know, that just changes the color of the ball. And that could be the case, but we know in fact that it is not the case. And the way that we know is something rather magical. The way we know is that if we take a second Pete box and we stack it below the first one, then what happens is, if you keep dropping black balls into the top, they all come out black from the bottom. And similarly, if you keep dropping white balls in the top, they all come out white. Now, can you see why this is strange? It's really critical that you do. You see, we think it's strange because if the black ball emerging from the first Pete box is some of the time white or some of the time black, then it goes into the second Pete box some of the time white, some of the time black. In which case, since both a black and a white ball going into the top of a Pete box produce a random color at the bottom, we would expect there just to be still random black or white balls coming out the bottom. Okay. Let me say that again because it's really, really important. If the way a single Pete box works is that a white ball comes out randomly black or white and a black ball comes out randomly black or white, then when I put two of them, one above the other, we expect that the ball coming out the first one is black or white, And so a black or white ball going into the second peat box, it doesn't matter whether it's black or white, it should still come out randomly black or white, but it doesn't. And that's actually a really mysterious thing. Okay. So what do you think we do as scientists when we see something like this? Well, our curiosity gets the better of us. We think, what color is the ball going into the second peat box? So what we do is we slightly pull the peat boxes apart and we just look. We shine a light in over here and we have a look to see what is the color of the ball partway, as it comes out of the first peat box and into the second. And now something that seems crazy when you first hear it happens. You see, if we see the color of the ball going into the second peat box, we see that it's sometimes white or black. And now we find that the balls that come out the bottom are also sometimes white and sometimes black. We go back to just having random colors at the bottom. Okay?
So looking at things disturbs things, and if you've had, interaction with just the classical world as a sophomore or as a dog, you probably are surprised at this point. Now, once he makes this clear, the point that I would like to make is that he introduces a way to calculate, which doesn't require numbers. So I will show it to you, and maybe I'll let him play some more a little bit. That's the peat box as it is in the beginning. That's the way it works. That's the calculation that he's going to go through. He's going to say that if we introduce this idea of a superposition, and if the result of putting a white ball inside is a cloud that has white and black, he says, don't read too much into this. It's not really a cloud. We call it mystic because it's mysterious and so on. Okay, so it's just something that says these are the outcomes. And if you take on the left the white, the plus state, and you feed it through the peat box, then it's very simple calculation results that a determined sixth grader could follow. And it gives you this, which has two possible outcomes, both of them white, therefore you recover the white. And on the left, you recover the black. So that's the kind of calculation that he is going to make and explain to you, and then he's finished. He only introduced superposition. There is entanglement, which is essentially necessarily wanting to use systems of more than one qubit. And I have to tell you about those because the order is important in the book. But that's basically what the book is about. This part where he introduces NOT, C0, and Hadamard. Then entanglement, where he does the CSH game. It's the only algorithm that he does in the book is the Deutsch. He calls it something else, and you're robbing a bank or something. And then at the end, he describes, consequences. So I am going to take you to, I am going to take you to the course that I teach every summer, which again is a boot camp for people who finished college, STEM degree, not physics. And now we are using it to reach out to high school teachers so they can teach their students. So then, if this is the thing, I am going to go to class notes and I'm going to go to syllabus. And I wrote a booklet, which I presented for the first time in March of 2024 at 6E. So hopefully the booklet comes to us right now. It's an 86-page booklet. What's the purpose? The purpose is to use a system that he defines in the book to cover the main topics that we would have in an 8-week class, and I'll show you the contents in a second. So it's called a little qubitzer, and has the following table of contents. We start with superposition, which is essentially what he told us. We talk about multiple qubits. We introduce phase, but only at the level of plus or minus. 1 qubit gates, we've seen X, NOT, Hadamard. Then we do 2 qubit gates, C0 is important here. Swap maybe as implemented through 3 C0s, which are reversed. We introduce entanglement, we produce entangled states. And then we talk about phase kickback. And this was really the topic of my presentation to you today. To jumpstart quantum computing, my goal in my class is to present 6 cases, 6 discrepant events. I want 6 cases where the classical way of programming does not give me what this gives me. So my 6 things are Bernstein-Vazirani, Deutsch, Yoja, which I do the way people at Virginia do, with money or tiger. You know, there are two doors, and behind those two doors you may have money, 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 tiger, tiger, money. Those are all the cases, and you can only open both doors at the same time, or you don't open any. And if you get a tiger somewhere, then you're done, so you shouldn't. We encode the oracle in quantum gates, and then we proceed to show how one query is enough, as we were showed yesterday. We then have, because we have entanglement, we have super dense coding. Grover search algorithm, where the starting position is a simple circuit of 2 qubits. So basically, I have 4 cards face down. One of them is a queen, the other 3 are not. How many attempts do you need? You don't know where the queen is, so how many cards do you have to flip? This is what I tell them in the very beginning. What's the justification for these algorithms? What are they going to give me? And I call them quantum advantage because at this level, they beat all the other classical versions of approaching the problems. So in general, you need 2.5 of an average. But with a quantum oracle, only one card, and you're done. The oracle does not generate the answer. The oracle only recognizes the answer. So still one iteration through the system, and you know where the queen is. So they do feel interested. How come? How is that working? Well, if I just told them, and then I say there's math associated, and if they had decided already that they don't understand math, then we have disconnected. So instead I say, hey, we have this book. And you can trace, you know, whatever the meaning of the word trace is, just follow along the bits, which as a computer scientist you like doing, and then you will see how it works. And that's what Terry gives us, this mechanism. So then I have teleportation, which for the first time I have to use any kind of qubits. So now I have to use amplitudes. I extend the system. I talk to him, he's okay. He doesn't say that his system is supposed to replace quantum mechanics or quantum theory. In fact, this is a book like the one we were shown today. This is the final destination for our students. But in the beginning, when they are lost, you know, we need to bring them quickly to a place where they would do that math without realizing that that's what they are doing. So once you have teleportation, you could do entanglement swapping. I haven't until this year when I'm going to, that's why I asked yesterday, Ilya, if ZX is giving you some kind of tremendous simplification with entanglement swapping. And the main reason for introducing either rotations, arbitrary rotations as primitives, or adding the amplitudes in the description of the misty states was for me to try to encode W-entangled states. Again, I looked at all the videos that John Watros has posted so far, and I say my students should be able to understand all of those. When they start P555 or doing P555, that should be easy for them. So he talks about W-entangled states. I can't do them with what I have in Terry's book. I will extend it. I need a reason. At this point, the best extension is through eigenvectors. I can't say, is there a state that passing through a Hadamard gate is unchanged? Instead, is there a state such that when I pass it through, it gives me the equal likelihood of finding black or white? So if you do the equations, are not that very complicated, it turns out that there must be some irrational number somewhere in front of the number. And so that's how we extend the system, and we say from here on you have to use numbers in front of those white and black balls. And then they say, can we just give up on the balls, just say 0 and 1? And at that point, they have made the transition to the math that you see in a book like the one by Tommy Wong. So the final thing that I have is the GAZ game, which doesn't require as much interaction. I mean, we had guest lectures last year, Maria Violaris from Oxford, where she has thought experiments encoded in Qiskit. That's always good for a computer science student. Can I see that in action? And then one lecture from Wolfram Academic Innovation Group. And they also worked inside a Mathematica notebook, and then they came up with an implementation of the CSH. So they saw it. But I like something where if I would like to prove that every time I win, so GHZ gives me that. So we have a version of GHZ with colors, and then we showed it to Terry, and Terry says, you don't need the colors, you don't need complex numbers at all. So he showed us another method, the way he has it in the book, where GAZ is explained in those terms. So this is the text that we use with the main goal of not staying here, but rather making the transition to Mike and Ike or Tommy Wong. So if you don't mind, I'd just like to play the last part of the,
So may I ask
yeah.
to get that book? That's what I would want to do in my class.
This one here?
Yeah.
Or the cues for one? This one, I can give it to you. I can. So then. No, I can send the link, and then you can send it to everybody if they want to look through this. Yeah. I'll give it to you in the next break. Yeah. You know what? I don't know. I don't search for it. So if you want the link, that's what it is over here. I wrote 60. It's my stuff. Yeah. It's all right. I'll give it to you, and it's absolutely no problem. So I would like, if you don't mind, now you know why I said that it's surprisingly effective, the system, because yeah, you got it. Okay. Qubitzer, yes. So I'm going to go where we were, which I lost. Where's the video? It's all right. Thank you for asking me. That's the video. I thank you very much for asking. So.
I appreciate Tom Long's book, but I don't want my lectures to be what he does, which is writing out the math.
But it's okay if you do that. That's my ultimate goal anyway. Until they get to that level. Yeah, the book is really good. Seriously. So can I play this? So we had the same issue, and I just want to comment on that. You have to recruit in the beginning. You have to recruit. You have to say to people, hey, this is an interesting class. You're not going to suffer. You're going to learn these things. Yeah. So you are one type of, but if you have a TA, they should recruit too. You should get one. And then if you have an undergraduate TA, they should recruit too, because their voice is different than ours. When they say you should take that class, the teacher is amazing, the content is incredible, and they will find out and say yeah or no. But okay, so this is an issue. This is an issue. People are a little bit afraid of new things, so they might not sign up. This is very, very possible. So another thing is to give them credit, like N&M credit. Can they get natural sciences and mathematics credit, or just mathematics credit? And if they do, then they say, well, I might as well try this new class rather than the other class, which was okay, but this is a new class. Why not? So as long as they get the credit they need, they will try it. So now I'm going to finish this up.
So the very fact that we've observed what the color was between the two peat boxes has caused there to be some kind of change that makes the ball come out the bottom, either black or white. Okay, i.e., our observations have changed something about the world. And we find, well, then we think, well, maybe we're just, while we're observing the ball, we're doing something which is just really messing around with it. So we try very non-invasive ways of looking at the color. We try gentler and gentler ways. And what we find is that if the method we use is so gentle that we cannot tell what the color is, then the peat boxes go back to behaving normally, i.e. black always comes out black and white always comes out white when we stack two of them. But as soon as the method we use is strong enough to tell us what the color was, then everything gets messed up and black comes out randomly black or white and white comes out randomly black or white. Okay, so how do we describe the situation? So actually in quantum theory what we do is we've built a formalism, some mathematics that describes for us how to talk about the ball when it's in between these two peat boxes. And this mathematics that we use, no one has ever found a different way of doing it. Sometimes we find things we think are different, but this is really the only way to do it, as far as we know. And in that mathematics, what we actually do is we invent a new word for what is going on with the ball between the two peat boxes. Because you see, if it was the case that the ball really was black or white, then it would emerge randomly black or white from the bottom here. So we know that somehow what is going on with the ball between the two peat boxes is that it no longer is black or white. So we can't use that word or. So what we do is we just create a new word and we say it's a superposition. And this is just physicists making up a word. Okay, we don't really know what is going on there, so we just say, well, we'll call it something different. We say the ball in between the two peat boxes is in a superposition, or it's a superposition of being black and being white. Okay, and the next thing we need to do is have a way to represent and to describe mathematically, because that's what physics does, what is going on with the balls as they go through the peat boxes. And the way we do that is as follows. We first kind of come up with a diagram that tells us how to describe after a white ball has been through the peat box. How to describe that ball as it comes out the bottom. Okay. But a white ball that comes out the bottom that we don't look at the color of it. And so we just have a diagram that does that. And I'm just going to draw it as a little cloud. And inside that cloud, I'm going to list both alternatives for the color of the ball. Because sometimes when we look at it, it's white and sometimes it's black. So our diagram has to capture that notion that the ball coming out of the peat boxes before we look at it is in some way white, it's in some way black. We say it's a superposition of white and black. And this little cloud, or mist as I'm going to call it, I'm going to call this the misty state of the ball because it's very mysterious. Okay? So this is the way we represent the ball that comes through one peat box. And the rule for what happens when a ball goes into a knot box or a subsequent peat box is then you just treat these configurations or colors of the ball, combinations of them, you treat them just as if they're kind of independent. Okay. Now, what happens if I put a black ball through a peat box? Well, something needs to be different because the initial color was different and somehow the second peat box knows that the ball initially was black. So we draw a cloud for this case as well, a mist. And now there's a distinction, and this distinction is really at the heart of the mystery of this mystery of quantum theory. The distinction is that we put a minus sign, a negative sign. Similar to when you have like a negative number, we now put a negative sign on the color of the ball. Okay, so this is just a strange thing. Maybe think of it as a negative label on the ball. I can't tell you why that arises, but nobody can.
So at this point, it's important to say this is a very accomplished scientist. It's not like somebody who says, I can't tell you and nobody can. It's not important, but still, he is the grandson of Schrödinger. So some connection with quantum mechanics royalty is there. It may not mean anything, but he found out about that at the end of his PhD studies. So I will show you what the biography looks on the Q's for Quantum web page. It's extremely funny, short and funny. But at this point, he doesn't say about this, but it's good to mention, I suppose, so that people would pay attention.
Okay, so this is really now the only distinction between the misty state of a white ball that comes out, an initially white ball after it comes out the peat box, and an initially black ball that comes out of the peat box. Now, why does this help us explain what happens when we do the two peat boxes experiment? It helps us because the rules of the mist are that if you look at a mist and there's different colors in there, then you just see one of the combinations of colors that are in the mist. And in this case, we would see with equal likelihood a white or a black ball. But the rules say if you don't look at the color, if you just send that misty state through a second peat box, then what you have to do is treat each of the colors in the mist, just treat them separately and independently. So send the white ball through and send the black ball through and just sort of treat them completely independently. So in this case you get a much bigger mist, okay, because this white ball splits into itself into a mist of two colors, of white and black. And this black ball also splits into two colors, white and negative black. Okay, so remember, a black ball by this rule over here splits into white and negative black, and a white ball splits into white and black. So you see that going on here. Okay. So this is just a rule. Remember, this mist, you shouldn't think of it as necessarily, it's not that we see a cloud come out of the bottom of the boxes or something. It's a diagrammatic representation of the mathematics we use to describe this experiment. Now, you know from just arithmetic what happens when you kind of add a positive number and a negative number. And in particular, if you have a positive number like plus 42, and then you add to it a negative number like minus 42, then you get 0. They cancel each other out. And exactly the same thing happens in this diagrammatic language, because what happens with the mist is that the edges of this cloud kind of...
You cannot replace the edges of the mist randomly. He doesn't say it here, but they are supposed to be at the same level of nesting, and also they should have the same cardinality. So it helps, if you want, to think that at every stage this thing is in fact a mathematical expression, and you can check to see if what you're doing is right or wrong. But what he's trying to say is that with the simple rules that he has introduced, students can in fact just do diagrams.
Fade away. A mist within a mist is just a bigger mist. So here we go.
Yes.
A black ball.
Gina is here. She had a poster last year because she taught a course.
Okay.
And she used that book. And then she had a poster, and from her poster I saw these boxes. And then I think the lady who just did the demo before you with the games, she also mentioned some of these. It's the same idea. You put the coin in or something and it comes out the other way, right? So I'm very happy you're showing us this because I've been curious.
Okay.
Right, but the way it's like, the way I understood it is there's a box and there are balls that are white and black, and they come in, and I guess there's some paint inside and it paints them black or removes the black out of it. But then he does use the minus sign.
That's right. He uses a minus for destructive interference.
So there is no like,
No what?
so this is not really a machine where you put the white ball in and it gets painted black, because
The machine is basically a beam splitter, for example. But he's...
how do you explain the minus? Because yeah,
He said that nobody can. He just said that nobody can explain the minus. But what I'm saying is the minus shows up and cancels the, because it's on the black. And therefore you're going to get two whites out of this. Okay.
complex conjugate, and we know how
Yeah.
M works, but that's where his analogy breaks up, and
Because?
students are gonna question it. So at that point, once you start introducing the minus or the bar above the
But
ball,
will they...
that's already starting to say
Will they question it if it's the definition of the box? It's the definition of the box. If you put a white in it, out comes plus, which is white, black. And if you put a black in it, it's going to be white, negative black. That's the definition. That's the matrix, in fact.
Negative black is not.
Part of the definition. It's part of the definition.
So can I?
Sure.
Comment something based on my understanding? This is the first time I'm being exposed to this topic. But maybe it's like imaginary axis. It's shifting between real and imaginary, rotating. So your vision is you're only seeing the real axis. The imaginary is there. So it's shifting between those two. And imaginary axis minus and plus can cancel each other along the imaginary axis. So you end up with real one. Whatever you are seeing is small.
Well, then again, you're getting into imaginary world.
But you don't have to explain it. It's the definition.
That's the point. Yeah.
It's the definition. And then go work with it. It's the definition. That's the matrix. Do you have a reason for the minus in the matrix of Hadamard gate? Why is it that minus there?
I know why it is, but
Why?
I'm trying to think of this as it's because
It's the same reason.
yeah, it's the reason he explained, but
That's
then
right.
I'm trying to teach without complex numbers and ignoring that y-axis.
There are no complex numbers. And he says that if you want to use complex numbers, in principle, you can use two qubits, one for the real part and imaginary part. So you could get away with that in principle. But here we are just designing a mechanism to show how we can recover the original ball.
Yeah, but the boxes are not real, so the boxes are like the definition.
They are real. People have built Hadamard gates. Pete has, right?
Oh, please,
Yeah, but any beam splitter is a Hadamard gate. So for example, hang on. I think the concern is genuine, so we should try to see if we can answer it. So,
we can watch this video later. How to handle student
yeah.
Comment on
All right. Oh, sure. Okay, Ryan, I guess, if you don't mind.
So
Anthony.
this is a great example, and I think so as the teacher.
So the question was, are these boxes real? And has anybody built them? So then in this case, these are two experiments where two Hadamard gates are being put next to each other. As I said, a beam splitter is a Hadamard gate, and you put another one, it comes back. If it comes in horizontally, it goes out horizontally. That's it, that's white. And if it comes vertically, then it goes down vertically, that's black. So this is an example in this virtual environment, though, where you would have two stacked Hadamard gates, but these are Hadamard gates. And all the opinions are totally welcome, and I'm very grateful for them. Yes?
The way these kinds of representations work that you're introducing. This is very useful because it displays it as something that students can physically relate to. And actually, although quantum mechanics is related to the maps, and you want to get to the map, I really think that having these physical analogies is not trivial, and it's important learning tool.
Okay, thank you so much. I have a quote somewhere over here. I don't know if I can find it so I can read to you exactly as it was written. So this is a quote from Piaget, I think. Children in the early years of primary school need concrete objects, pictures, actions, and symbols to develop mathematical meanings. The same, I think, is true of students who lack a certain background or affinity for the abstract structures of mathematics. And that's where I thought the simplicity of the Misty State formalism is going to help my students. Now, that was my goal, to show you that there is a method that somebody introduced, and if you find it useful, you can use it. And if you don't, that's totally fine. And I found it useful, and I said, well, I'm not sure exactly to the extent to which it will be useful. And I showed you my little booklet, which covers the various cases that I'm trying to explain. They work for me, and hopefully they might work for you as well. So what did I want to do for you today? I basically can say I could have gone here, for example, and erase all of this. or actually erase some of it, for example, this, and say, although, this is a simple system, but you might have a reaction. I mean, it depends on who created this reaction. You are partial to the math formulas that you know already. I think you're going to favor it forever, and that's fine. There is a place over here where I quoted from here. Again, I don't know where it is, but I might find it before the end, where he says, I'm not trying to tell everybody to replace this, to replace quantum theory with this system. This is a quick way to bring people who don't know, who are afraid of math or do not know, have not done extensive math, to the middle where math is in fact happening, and hopefully convince them that they are not going to be unable to do it. That's the goal. Eventually, we are going to convert from white ball and black balls, or W and B, as he writes in the book, to actual numbers. So particularly every single time that we talk about something, we say, does this work? And we write it in Qiskit. And then Qiskit produces the wave function, which shows up in the traditional sense, just numbering is different. And then I say, would you calculate it with Misty State? Okay, is it the same formula? So as they proceed through this, they learn to convert between Misty State formalism and regular math consistently, every day. And so at the end, they know that they should convert to the mathematical formalism and stay with that one. So here, if you want, I could just calculate some of these things to determine, for example, that if you start with a plus, you will go back to a 0, but you've seen that already, I suppose. Or if you start with a minus, you can go back to a 1 with a thing that you've seen, and the z applied twice to minus is going to give you a plus, and so on. So we can do these calculations if you want it. Now, the exercise that I start with, the exercise that you could also see here today, is a simplified version of Bernstein-Vazirani. So what you have in this case is a black box which has a number of C0 gates, and they are connected with a target at the bottom and with the controls somewhere. The order of them doesn't matter, but I put a musical score so that reminds me in what order I ordered them. What you will need to do here is to feed inputs and determine, based on experiments that you do here, what exactly connections you have on these wires. So one option would be to say, I know how a C0 works, and I'm going to put a 0 on the bottom, and then I'm going to try the lines one at a time. I'm going to put a 1 on a line, and if I get it, if I get to change the target at the bottom, then I suppose this line has a connection, other one it doesn't have a connection. So I try them one at a time. The complexity of this is linear. I have to make as many tries as wires I have in this box. Can I do better? The answer is yes, you can do it in one step. Well, how exactly am I going to do that? You notice that if the gates were backwards, then you wouldn't need anything. You would just feed a 1 at the bottom and put zeros everywhere, for example. And then the zeros will be changed only in the places where this thing is, in fact, a target connected to the bottom. But that's not the case as we have it here. So, so I say there is a phenomena that you could prove. This is an extensive exercise. It's not as simple as h of white is equal to white and so on. It's called phase kickback, and it simply says that if you feed let me show you the this is it. So if you feed a plus and a minus, where the plus is in fact on the control, the result is going to be minus minus. So instead of the target changing, the control changes, which is a behavior that's a little bit counterintuitive with respect to the control not. So this is an exercise. Now that you've seen all these videos and you've watched, you've read the book and you've done my exercises, can you prove this? So in this paper, I do have a proof of this in the exact formalism that he has in his book, where I use clouds and I show how things are happening. So I hope you recognize the plus and the minus that we talked about earlier, and the plus goes into the control input, and then the target has a minus. And what I need to show is that outcome will be white, black with minus, and then white, black with minus. So I explain how things are being transformed, and in the end, I prove it. What does that mean? If I can prove that a plus on the control with a minus on the target actually produces two minuses, is that useful? Maybe you don't see that it's useful, or maybe you say, that solves the whole problem. So the idea is to use a Hadamard gate on the inputs so that you convert your inputs from zeros and ones to plus and minus, and use the plus as the bit that I said I would have used if the gates had been connected the other way around. So at this point, the Mr. State formalism is not needed anymore, but it was needed to prove the phase kickback. And you say, well, I wanted to see how the phase kickback works. How do you do it? You just multiply the matrix, or where do you find the reason for that working? So in this particular approach, I said, well, we have committed ourselves to the Mr. State formalism. I show you, or I give you as an exercise to prove phase kickback with the Mr. State formalism. Now I'm out of the formalism, and I just have this circuit which gives me the outcome in just one step. So it doesn't mean anything unless I can write a program that would produce the same thing in an objective way. So at this point, I can write this program, or I can write something like this and put it in Qiskit and show you that if you run it, it produces these outputs. And so that would be one case where I had an argument and I had a formalism that you can follow along with the pencil, and then at the end prove that the Qiskit will give you the same thing also. One thing that doesn't appear in the book, so if you, I don't know if this is convincing or not, or if it matters anymore, I try to sort of answer to address the questions that came up. And like I said, I'm not saying you should use this because it's the best thing in the world. I think you should try it because I found it very useful. And if you don't find it useful, I think you should let everybody know, and that's still okay. So in the book, you may decide to start writing Misty States in some fashion that is different from the way he came up with those definitions. Because, hey, you read the book, you understood it that way, and so you can create states like this one that you can describe to other people. For example, this one that you see over here is a superposition between a white ball and a superposition between a white ball and a black ball. And now the question is, what does that mean? And can I reduce it? And the answer is, can I actually simplify it? Can I wipe out the margin of the cloud? The answer is you cannot. Because as I told you before, when you want to embed Misty States into bigger Misty States, they have to be at the same level and they have the same number of states inside. So in this case, I have a state that basically is it. I cannot change it in any way. But if you apply Hadamard gate to this state, you realize that by the rules of linearity, as I show over here, if you want to look at it, this state transforms into itself. And there is a term for that. If this is a vector, because it is, then h applied to that is that vector, then this is an eigenvector. So at least you can introduce those terms. Even though the state is like irreducible, whatever that means, I cannot reduce it further. Like in under calculus, I cannot reduce the terms. I can work with it, and I can prove that it's a fixed point, which I think a computer science student understands. And then from here on, you could just move on to thinking about them. Up to this point, I can show you what the eigenvectors of the NOT gate are and tell you why they are important, and the eigenvector of the Hadamard gate. And then I can create states that will surprise you from the point of view of, say, classical probability. So this example here shows that if you were to superpose an apple as a possible snack with a snack where you're going to get either some watermelon or some cherry, because these things are different, you're going to get the apple with 50% probability, and then you'll get the watermelon with 25% probability, and cherry is 25% probability, because they are different. But then if you put an apple instead of the watermelon, the probability of an apple is not 75%. It's going to be 85%, and that's because there will be interference between, you won't know exactly, did I get the apple from the inner superposition or from the outside superposition? So if they find, this is, I think, the simplest example in which probabilities don't participate the way we are used to, then can you come up with an example that will show that happening? And then the quantum flytrap says, as I told you in the beginning, we are good at picking up intuition as long as we can work with that world, but we are too big for the quantum world, so you can use quantum flytrap. And then here's the situation where I get 85% apple and 15% cherries. But am I sure that this is actually coming from the 25 plus 20, 25 plus 50 plus 25 plus 25? The answer is, if I take this, which gives me 85% of an apple and 15% cherry, and I try to measure before interference is happening, then I get a 50%, as you can see on the first line, and then you get 25, 25 on the bottom line. So I'm saying that in the process of using this formalism, we can actually make bridge the gap between I am teaching you some meaningful quantum concepts, quantum computing concepts, and you can take the basic algorithms with just 2 or 3 qubits and follow along what's happening if you are interested, and you will have an idea as to what those circuits are doing. But at the same time, I can build little experiments for you to say, so this is what I would experience if I were to be small enough to sort of play in that world. So here's an exercise. I think I'm getting close to the end. It's 11:51, so I have until 12. I might as well end now. Let's end with an exercise. Let's say that I told you that I can represent eigenvectors for the Hadamard gate easily. You say, oh, I'm scared of eigenvectors, and I don't quite understand what those are. What are you trying to tell me? And I say, you are computer science students. Do you understand what a fixed point is? F of x equals x. Well, that's what I am talking about. I'm talking about a particular value that a function is applied to, and out comes that value with a plus or minus some scalar in front. So they say, that part I understand. Then I say, hey, build a circuit that gives me the eigenvectors of the Hadamard gate. You know, the Pete box. So there is a way to build such a circuit as only 1 qubit, but you need rotations. And I didn't give you rotations. But you say, I need rotations. OK, put them in as a primitive. Now you're going to say, why do I use rotations? Well, because matrices, and then I have to necessarily make the transition to actual math. I need it because the thing that you taught me so far doesn't have that in. But another alternative is, how about I allow you to build a circuit that maybe has 2 qubits? Can you then produce the eigenvectors of the Hadamard gate? And in this case, look at this circuit. This is a circuit that shows that you can do that, but not the way you would do it in classical programming. In classical programming, you are very calculated and you are very exact. You have a proof. Everything should happen deterministically, exactly as you anticipate. This one works differently. This one is, in fact, going to run, and then you measure the first qubit. If you get a 0, one of the eigenvectors is on the other line. But if you get a 1, the other eigenvector is on the other line. So that's a little bit unusual because you don't know what you're going to get until you measure the first qubit, and then you will know what you got on the other line. So like, I'll cook for you. I'm a great chef. What can you cook for me? Lasagna or bouillabaisse? OK. Well, cook something for me. Well, you will not know what I'm cooking for you until you measure the first qubit. So that's a little bit weird because we postpone that decision. But this basically is an example that will force them to say, if I know some classical computing, chances are that when I look at these circuits, they will behave in ways which are slightly different, and therefore I need to be ready for that. That's the whole point of this, where I'm not trying to negate or deny the transition. In fact, I am trying to accelerate it or facilitate it. And that's the whole purpose of this presentation. So I personally like this approach, and I use it, and I try to extend it to make it useful. That's basically it. Thank you.